I didn't catch that. What was that?
We might want to ask everybody to mute as well.
Oh, yes. Yes, most definitely. We would like you to mute. Although I can go ahead and mute everybody myself at some point.
You've got the power!
Something like that. Okay, well, I'd say we have a pretty good crowd here today. So I think I'll introduce our speaker. This is Professor Sally McArthur, Professor of Biointerface Engineering at Swinburne University of Technology, who is joining us early in the morning in Australia. And she is also the editor of the AVS journal Biointerfaces. So I hope some of you have seen Biointerfaces and consider contributing to it in the future. So with that, I will turn it over to you, Sally, and go ahead.
Thanks so much, Jeff. That's brilliant. And good morning, good evening, good afternoon, good whatever. I have coffee, so it'll get better as it goes, as that starts to hit. It's 7 a.m. here in Australia, so hello from Thursday in Australia for those of you who are joining. And thank you so much for joining. So what I thought I'd talk about today is try and cover a broad area of things that I do here in Australia, but also for the students who are joining, I'm happy to answer any questions on careers and partnerships and collaborations as well that I do. Part of my role here in Australia is actually as a CSIRO science leader. And for those of you who aren't aware of what CSIRO is, it's the Commonwealth Scientific and Industrial Research Organisation. It's our national labs. So I'm part of the manufacturing division there, which is fabulous. I have a joint appointment. I'm 100% employed by Swinburne University, but I spend half of my time at CSIRO working there with a team. And I'll talk a little about the project work that we're doing in that area as well. But to start with, let me explain. Okay, for those who haven't been to Australia, why not? I know not right now, but in future, we'd love to see you. So we're here in Melbourne, down in the bottom, and let me get my mouse on the screen, down here in Melbourne. And my university is just outside the Melbourne Central Business District. It's on a train line, and it takes about 4 stops from the city, so it's about 10 minutes. So we're on a suburban campus. But we're also a dual sector university, and that in Australia means that we have vocational education as well as higher education. So we go all the way through from more the community college type education styles all the way up to PhD. So it gives us a really interesting way of looking at both the educational needs of businesses and employers, as well as the research needs of a wide range of different things, and allows us to connect all the dots in between, which is really good fun. So this is our campus right in the middle of a fairly busy street normally, and we just look back towards the city as well. So that's us. This is Melbourne, for those of you who, again, aren't quite sure what it might look like. Not quite like this today. It's a little colder and darker right at this point, but, you know, one of the world's most livable cities. We tend to duke it out with Vienna and occasionally Vancouver as a livable city. So what do I do? Who am I? I'm a materials engineer by my initial background training, and I've worked in biointerface engineering for quite a long time now, and working across quite a range of different areas where I get to take my skills in coatings and characterization all the way through. For those of you who know the University of Washington and Dave Kastner, I postdoced there for a couple of years, which is where my some of my skills in surface analysis come from, and a lot of my interest in how do we make everybody do surface analysis comes from as well. So my team over the last 10 years and 15 years have been all about connecting biology and technology and doing that interface between how biology interacts with different technology platforms. And so we look at fundamentals from proteins and lipids and cells and bacteria on surfaces, for looking at how to make better tissue engineering, how to build membranes or make wound dressings that prevent bacterial attachment. That's what we've got down here. We've got bacteria growing on an electrospun scaffold, and I'll talk about that a bit more. We also work in areas like bioarrays, so controlling where biology goes on surfaces, for sensing applications and microfluidic devices. And then into something slightly different, we work in bionics, where we're doing work with optical stimulation of nerve and other tissues as well, using gold nanoparticles. So that's with colleagues here in Melbourne. But at the heart of it all for me, it's about how do you actually know that what you've done is real and what the interactions are. So that ability to bring together the characterization techniques in different ways to make sure that we're quantitatively characterizing the system that we make. So that might be biological characterization, it could be physical characterization, the mechanical properties, chemical characterization, and then obviously a huge range of tools that we have. We love a toy that we have to actually bring it together. But critically, understanding how they work together, how these different techniques give us different parts of the story, which is really important as well. So let me start with just talking about surface modification in the MedTech sector and the biotech sector. Obviously, in MedTech, we choose our materials to make our devices and our substrates out of because they have specific optical properties, mechanical properties, or other characteristics. They might be price point as well. So we can't just say we can make a perfect coating for gold. That doesn't work for us. We need to have coating technologies that actually are quite flexible and might need to be applied across a range of different materials to enable us to actually implement the technology, because the devices may not be made out of just one material. In terms of the types of things we want our surfaces to be able to control, we'd like them, in the most part, to control protein surface interactions, so which proteins go down and how they absorb, how they present themselves to the world, and how the world sees them. And from that, that's how we can control cell surface interactions, when cells attach, when they grow, how we can stimulate them to grow and form new tissues. And then if you look at more of the biotech sector, the immobilization, the presentation of biomolecules and other systems and polymers in a controlled location, time, and with, obviously, a functional retention. At the heart of that, that means we really need systems that are non-fouling. Sometimes they might need to be hydrophobic or hydrophilic. We want to control those types of characteristics. A lot of the time, to immobilize a biomolecule, we want them to be amine reactive, that is, react with amines or enable us to immobilize via amines from the biomolecules. The other thing is, these are not dry systems. Most of the time, they're working in some type of aqueous environment. Now, it's not a complex, well, it is a complex aqueous environment, but it's still mainly water and a bit of salt. But it's amazing how many coatings don't like being in a bit of water and a lot of salt. So that's something we also have to think about. But also with devices, they can sit on a shelf for a long time. So they have to be stable in those environments for quite long periods of time. And obviously we want to limit any toxic events and trigger, and we need to be able to trigger quite specific responses from our materials as well. So, you know, not too much for a surface to do, just, you know, everything. So one of the techniques I use a lot is plasma polymerization. Some of you will know it more as PECVD, but in the way that we use it, it's a very soft version of PECVD rather than the technological PECVD techniques you might be used to with silanes or other sort of hard coatings that are formed under those systems. We do a lot more tickling of our monomers. We're using low powers and we're looking to retain monomer functionality rather than create a thick film or deposit a lot of material quickly. So we're looking at films that are going to be in the sub 100 nanometer range. But we want to be able to use those benefits of plasma polymerization where we can coat virtually any dry substrate. It's relatively simple. The advantage for biology is if we have a plasma polymerization set up in the right lab, it can be sterile and we can maintain it being sterile as well. But critically, lots of different chemistries. And so the types of chemistries that we work in, and my lab actually runs a open access service for industry and researchers that anybody is able to access from anywhere in the world, is we have acrylic acid to create acid groups on the surface, allylamine to create amine groups, octadiene to create hydrocarbons, allyl alcohols, the glymes to create ethylene oxide type surfaces. But we can also do things that are less common, and there's systems that in plasma polymerization, the monomers wouldn't traditionally form polymers. They're not polymerizable in the terrestrial sense, but by using plasma polymerization, we can actually polymerize them quite effectively. We just have to, and I'll talk about some of how we've thought about that. So less common things are maleic anhydrides, epoxies, thiols. If you really want to evacuate your building, you put a thiol in and don't control your gas outlet, and you cold trap thaws, and you end up with a quite a horrible no friends is actually the way that ends up. But all of these systems can be a foundation for immobilization, or we could use them alone. So they can either we can either immobilize directly onto the plasma polymer, or we could graft polymers or other biomolecules onto the surface and then graft from there as well. We do a lot of work in the lab on how to monitor these systems, how to convert them into technology applications such as reel-to-reel for carbon fiber coatings and other things like that. Happy to talk about what work we've done there, but it won't be in today's talk. So one of the interesting questions that we have with plasma polymerization is our goal is in retaining specific chemical features within that are found in the monomer and translating that into the thin film that we form. And you'll note that I'm being really careful about calling it a polymer. It's a network, a polymer network. It doesn't form your traditional polymer structures. You get more of a complex network of fragmentation and reorganization driven by different interactions with reactive species in the glow. But there's a lot of debate in our community around the conditions that you use in depositing plasma polymers and the sort of power conditions. And there's some groups that swear that the only way to do it properly is to pulse the plasma. Other groups talk about just depositing it with a continuous wave energy. Then you get into what are the right duty cycles, the average powers, what does average power mean? Should you be pulsing at milli or microsecond pulsing? And at which point I sort of wanted to scream quietly in the corner and rock. But there are also issues with the types of pulsing that you do and the ability to monitor that pulsing. A lot of people pulse systems, but they're not actually looking at the way the energy is delivered actually in the chamber. And that's an interesting question, and one that we've looked at in the past, is that when you're doing a pulsing regime, what we found is you can have delays in your system. So you have your trigger signal, and then you can probe using an electrode probe inside the chamber to look at what is actually happening. And when you look closely, you can actually see that there is a delay in the actual signal going through. So if you use just the pulse to actually determine what your duty cycle is or the power that you're delivering, you can actually have quite significant changes in the amount of power that's going into the system if you don't take these types of delays into consideration in the system, particularly when you're doing millisecond and microsecond pulsing. Those delays can be a significant part of what you do. They can also be really closely affected by how quickly you're pulsing and the recovery process within the chamber as well. So this gets into your fundamental plasma physics, which I will admit right now, I am not the guru in. I am just the curious person who likes to know what's happening in terms of measurement science as well in our system. So what we wanted to look at in this study was to actually look at maleic anhydride. It's quite a complex chemistry. It's a ring opening to get it to polymerize. And so that's the classic way that you polymerize it nicely. You get a film, but you have no anhydride reactivity in the actual film. And so for a long time, people had been debating what are the right conditions to do it in. And so what we did was did a study on same power, same average power in the system, so 1 watt. But we wanted to look at different pulsing regimes and different power delivery. So continuous wave power, either a millisecond or a microsecond pulsing regime. And what we do in this system for maleic anhydride, we have chambers that are metallic, so we have to heat the monomer because maleic anhydride is not particularly volatile. And then the chamber is just warmed slightly so that we don't just condense the monomer onto all the walls of the chamber at the same time. And so if we look at the XPS, this is our first XPS profile for the talk, yay! We're looking at the different types of power distribution. So if we look at, this is the carbon 1s profile, so we're looking for those oxygen-containing species that are formed in the plasma. And you can see straight away that it's quite a complex oxygen-containing species. If we start with our 1 watt continuous wave, so we're just depositing a film at 1 watt, it's very low power, and we get chemistry that you can see we've got quite a complex range of oxygen-containing species. And I have to admit, when you're fitting something like this, it's not the easiest thing to fit. There's not a lot of features there. You can fit absolutely down in the 289 range for your esters and ether, your esters. And then you've got a beta shift down here that you can put in, and everything in between is more, what are your trend, how do you like to fit your data? But there are definitely more complex oxygen containing species, some esters and some other groups in there as well. Now, the key thing that we used in tracing this, obviously, is because in XPS we can't detect hydrogen groups, we're looking at this area as being indicative of anhydride groups, but it could also be indicative of carboxyls being formed or those ester groups being formed as well. So we have to be careful on the interpretation here. But as we move through and we look at a millisecond pulsing regime, so all of these, if we do the calculations, are a 1 watt equivalent deposition. So we take the power up to 10 watts, but we pulse it for 10 milliseconds on and 90 milliseconds off. So the power is delivered in pulses, and you can see that we get more, the introduction of more of what we are associating with anhydride groups in the film, so we get more retention of that. And then if we go to, again, the peak power of 10 watts, but now we work in a microsecond, microsecond regime, and we go for 80 microseconds on, but 800 off. So a very short burst of power and a long time for all of that energy and the reactive species to react and actually form a polymer on the surface. You can see, again, we can see the introduction of a higher contribution here in this domain that we're associating with anhydride-like species in the system. So this definitely tells us that the difference between, that there is a significant difference with how we pulse the system here as well. Now, obviously, if we're looking at actually defining the difference between it being an ester species or a anhydride group on the surface, we need to actually look at its reactivity. And so we use trifluoroethylenamine to actually react with the surface. It's done in the gaseous phase. And so if you react that species on the surface, if they're anhydride groups, you can actually get that to react, and you'll get a lovely fluorine tag on your surface. So how that works then is you can use that amount of fluorine to give you an indication of how much and how many anhydride groups you've got on the surface with that ring opening reaction. And you can see clearly here as we introduce more fluorine as we get up to the microsecond regime. Even though the millisecond data looked like it was introducing more oxygen and more anhydride groups to the surface, they're not reactive. That suggests that they're more ester groups on the surface rather than anhydrides due to that ring opening and reorganization that occurs in the plasma process. But once we get to the microsecond regime, you can see we can start to introduce quite significant levels of fluorine into the surface, and so we can, that suggests to us that we've got reactive anhydrides on that surface, which is all great. But obviously, we have other techniques we can use as well. But what I wanted to jump to here, and that sort of gives us an idea of how we use the XPS to probe these plasma polymers. But the piece I wanted to talk about here next is actually how we can use these plasma polymers to create patterns as well, and how we use then different methods of analyzing them. So the work that we can do in here is to take your basic photolithography approaches, where we take one plasma polymer, spin the photoresist over the top of it, just any of the standard photoresists, do the light and the standard resist development, and then deposit a second plasma polymer over the top to create and then remove the resist and have a dual pattern plasma polymer. Now, one of the interesting things when we set out to do this was that I was pretty sure that the resist process was going to just either remove, damage, or significantly challenge our plasma polymers, remembering that we're not making these technology hard, rigid, heavily, densely cross-linked plasma polymers. We're making quite soft ones with actually quite high functional group retention, and we're actually interested in the properties of those functional groups. But the interesting thing to come back again and look at these types of things, and now I introduce a little bit of TOF-SIMS to the picture, is we can pattern that anhydride chemistry. And this is a maleic anhydride now patterned onto a tetraglyme surface. So this is a ethylene oxide-based plasma polymer. And if you actually do, again, that derivatization experiment to look for where the fluorine goes when you functionalize the surface, you can see that we can successfully, quite cleanly pattern the anhydride onto the surface, and it's still reactive afterwards, which I found fascinating, because the last thing, this has had all of those processes done to it. It's had UV light exposure to do the development of the resist. We can take the resist off, and the anhydride group is still reactive on that surface in those brightly lit areas, because they're the fluorine areas are bright here. And the nitrogen containing species, this is negative ion, TOF-SIMS imaging, and the nitrogen containing species also correlate with the fluorine, so that gives us another way of looking at this. The pieces in between aren't patterned and aren't picking it up, indicating that the glyme surface is not reactive to it as well. So we either haven't damaged the glyme surface, that's our assumption from here, but actually we've got positive ion TOF-SIMS images that show us clearly that the tetraglyme is still there. And we did a lot of work in this area proving that these coatings are stable under these types of conditions. But the real test, obviously, is when you put it into use, and now you've made a maleic anhydride pattern on a tetraglyme background. The tetraglyme, nothing should stick to. No biomolecules should stick to it. The maleic anhydride, the anhydride, should react with amine groups in a protein and allow us to actually immobilize proteins on our surface. So here's some TOF-SIMS imaging, where we're looking in the top range here of where the amino acid related peaks are in the top here. So this work is the bright areas are where the amino acid related peaks are found. So that indicates that there's protein attached to the surface. And then in the bottom frame where the A is highlighted and the outside is highlighted, these are the peaks that are directly related to the tetraglyme plasma polymer, and they indicate that there are no proteins attached to those areas. So where the non-fouling surface is, it is still non-fouling, and where the amine where the anhydride containing region is, the protein is actually immobilized. So it's a functional coating, enabling us to actually pattern both the chemistries and control where proteins go. Tick, tick, if you remember back to my initial list of things I'd like my coatings to be able to do. The fascinating thing here is the level of processing that we've actually done to this. This has gone through all of those standard lithography processes on two quite sensitive plasma polymers, and they've stood up to, and they've still been able to be functional at the end of it. If you think of all the stages that go with doing photolithography on surfaces, there's quite a few different chemicals and processes that go on there. The other really exciting thing I think with this is that because it is using a photolithography process, and plasma polymerization is an inherently scalable technique, you can start to see how these techniques blend into manufacturing processes as well. And that's one of my passions, is that how are we going to actually make this? You know, is it that I can make a couple of these in my lab, or can this actually be scaled into manufacturing processes? And obviously with the semicon industry, we've got all the tools to actually think about how we integrate these types of coating technologies directly into manufacturing processes as well. And so the other interesting thing is those coatings were all done on silicon wafers. We love a silicon wafer as a control surface. We can do it on a range of other hard, rigid surfaces. But polydimethylsiloxane, or PDMS, silane-based materials are beloved of the bioengineering community because we can make devices and microfluidics out of them quite quickly. We get small-scale ideas tested. But putting plasma polymers on top of these silane-based materials or silicone-based materials is really hard because of the creep. So you have a lot of unreacted monomer, and we all know once we have silanes in our lab, we have silanes in our lab forever. And as surface scientists, we tend to, it is the verboten, do not bring these things into my lab. But the ability to actually put our plasma polymers onto these silicone elastomers was one of our big challenges. And so we've developed methods for doing that and for preventing that creep. So what we do in effect is use the plasma polymer layer to trap the low molecular weight monomers within the actual coating, and we have a station of a way of actually doing that, so that we can then go on and pattern plasma polymers. And so what we're looking at here is a silicone material where we've deposited that same chemistry that I've deposited onto the silicon wafer. We've got maleic anhydride and tetraglyme on the surface, and you can see here the bright areas in the top image here are from where we've immobilized proteins onto the actual, this is TOF-SIMS imaging, onto the surface of the anhydride. And here in the bottom we can see the bright areas are where the tetraglyme is, and there's no protein absorption here. Now, and we can obviously then translate that over into a fluorescence image where we fluorescently label the protein, or we put a fluorescent antibody to the protein onto the surface, and that then detects. And so we've got bright areas here where the protein is stuck, and dark areas where no protein is attached. And this is the tetraglyme area, and this is our anhydride area. And we can do this within, actually deposit this into channels and into silicone microfluidic platforms, or build up devices that way as well. So this is getting to that point of why plasma polymerization. The other thing I wanted to say was that if you've got all of that going on, and coming back to the point around the power question, is that we can use TOF-SIMS to actually separate and understand a bit better how our coatings are working. So if we look at all of the data, and we do a lot of principal component analysis, mainly because I come from the Dave Kastner School of TOF-SIMS at University of Washington, and it's a great way for looking for what causes variation in your TOF-SIMS data rather than the huge complexity of peaks that you get in your TOF-SIMS. But if you look at a scores plot where you compare spectra collected from the 1 watt to spectra compare the millisecond pulsing and the microsecond pulsing, now we could see from the XPS that they were different, but the TOF-SIMS gives us the ability to say, okay, we can see chemical differences at the molecular level now, not just at the elemental or oxygen containing species. And when we look at the loadings plot, we can start to see that if we just compare continuous wave to the millisecond and the microsecond, they split, and you can see the actual components of the system that are making it up. So we've got some ring opening and different features, and that unsurprisingly groups the microsecond and the millisecond data together compared to the hydrocarbon species that are more prevalent. These are the peaks that cause differences between the spectra, not the peaks that are the same. But if we then just look at the microsecond and the millisecond, you can start to see why that fluorine reactivity was different between the microsecond and the millisecond, because it's the microsecond plasma polymers that actually contain the monomer and the reactive monomer that is present, and the anhydride groups in the surface as well. And that then got us on to thinking, what is the actual, how does that monomer break down? What is actually happening, and how does changes in that duty cycle, so we could pulse these systems in lots of different ways. We can keep our on time the same and constant at 80 microseconds, but if we change our off time, how does that actually affect the monomer and the monomer breakdown process? So we're holding our time on and then changing our time off. Now, obviously, that affects the duty cycle and the amount of power in the system. But if we look at it, we can clearly see with the TOF-SIMS, by analysing the coatings that are produced from those things in TOF-SIMS, we can clearly see that that quite neatly separates out each of the chemistries. So there are variations in chemistries with those off times being varied. That's obviously coming down to very slight changes in the total power in the system. So when we look at that more generally, we can see that if we start with what causes ring opening, if the average power in the system is is higher than about 3 watts, and that correlates to an off time of about 50 microseconds, we see full ring air opening. So our TOF-SIMS data shows us the specifics of the chemistry. We get functional group loss when we're between about 1.7 and 3 watts. So that's off cycles of around 200 to 400 microseconds. But we see functional group retention when we've got 80 on and either 600 or 800 off. So that's somewhere between 0.9 and 1.2 watts. Now, we lucked out, obviously, when we started looking at this study, because we picked 1 watt as our average power that we wanted in our system, and it just happens that that gives us the best sort of functional group retention. But it's, I think, really important to understand how much flexibility you've got in your system. So we could drop it down to a 600 microsecond off, and that then starts to play into the cycle time. When you're manufacturing these plasma polymers, you really want to know how much you can speed up your cycle time in your process as well. So the other thing I wanted to say is the photolithography methods that we use give us a really great way of micropatterning our plasma polymers. But when we start to look at biology, often what we want to look at is nanoscale features, and we want to be able to control molecules maybe more on the nanoscale. And so what we pushed just recently, and we're just publishing this work at the moment after quite a while, is using EBL actually to pattern on the nanoscale, and using EBL writing as our method of direct writing onto a resist. So in this case, again, it's the exact same structure that we use with the photolithography, but we're using now a PMMA resist on our system and writing on the PMMA with the EBL. You can, and there has been work done where people have used the EBL to directly write onto the plasma polymer. So you can imagine the plasma polymer actually being a resist. But in our case, because we want two chemistries to be patterned and we're interested in the chemistries of the plasma polymer rather than the underlying material, we're PMMA resist, EBL writing, second plasma polymer on, and then we can create a pattern at the end here where we've got two plasma polymers patterned next to each other. But the EBL gives us the ability to look at how small a feature can we actually reproduce in this. Obviously, the process of actually removing that resist when you're at the nanoscale is the challenge here, because you've got quite a thick layer of resist and a relatively thin and soft layer of plasma polymer sitting on top of it. So part of the question is tearing of the actual plasma polymer, lifting it off, delaminating it from the surface at the same time. And that's pretty much what we saw. In this case, what we've done is we've deposited a polyallylamine coating, an amine coating on top of an acrylic acid plasma polymer. We're using an ITO substrate because of the EBL requirements as well. And you can see what we've chosen to do is long lines that allow us to locate the feature that we're interested in. And then we're just using a gradient of the sizes of the actual patterns that we're drawing in using the EBL. So that goes from around a 900 nanometer line, or actually it's I think a 1 micron line, down to, and you can see the line here, it says it's a 50 nanometer line here, and then we go to a 20 and a 10, and this is optical lithography, optical profilometry, looking at the surface, and you can see quite clearly we've got there's differences in the lines, but we actually are interested in the chemistry. And so that's again where TOF-SIMS comes into the play. So the interesting thing for us is that this is right at the boundary of where your traditional TOF-SIMS instrument works. The resolution and the spatial resolution of TOF-SIMS typically is quoted at the 100 nanometer level for inorganic materials. For organic materials, we have a lot more trouble. But there's sort of a dual thing here of actually pushing the boundaries of the spatial resolution that we can get out of the TOF-SIMS imaging and the scale of the patterns that we've got. And you can see here in the first instance, the thickness of that plasma polymer film that we're depositing in that second deposition actually matters. So in this side here, we're looking at a film that's been deposited on top of the allylamine of acrylic acid for 10 minutes. And then in this side, we've only deposited for 5 minutes. So the film is half the thickness. For us, that 10-minute film would probably produce a coating that's about 40 nanometers thick. So 5 minutes produces a film that's about 20 nanometers thick. There is just a direct correlation between deposition time and film thickness. So you can see a number of things in this image here. When the film's thicker, you can see we've struggled to delaminate it. The boundaries, you can see there's tearing associated with removal, and you can see that we're struggling to see the resolution at these smaller features. Whereas when we drop the film thickness, that second coating's film thickness down, we can start to imagine, if I squint really hard, that the 50 nanometer line is still there, but the 100 is absolutely there, the 200, the 300, the 400 as we move through. And so we can see the chemistry, and we can see that the pattern resolution is better under those conditions. And so we're absolutely able to get to submicron patterns in this way. And the really interesting thing with all of this is that we're able to demonstrate chemistry differences. So what this is actually looking at in these images are fragments that are associated with the acid-containing chemistry on the surface. So the acid pattern is the lines. The background is allylamine, and we've got data that shows that that is absolutely still allylamine there in the background. And the interesting thing is that the order in which you pattern matters as well. So when we put the acrylic acid onto the allylamine, it works really nicely. If we reverse it and put allylamine onto acrylic acid, not so much. And so you can start to see here the acrylic acid film and the allylamine lines, the acrylic acid has actually lifted off the surface. And we've, the allylamine has lifted off the surface as well here. And
we have a question. The question
yes,
is,
sure.
in slide 21, is the reason you sum the two masses to get more signal for imaging?
Absolutely, yes. It is all about summing the masses. So we could actually, and what we have done is gone in and done some multivariate analysis as well of the images. The challenge you've got with imaging is the way this data is collected to get high spatial resolution means that we have poor mass resolution. So we can't get into, in these images, the data that we use to do multivariate analysis needs to be highly, have high mass resolution. And so we haven't been able to produce much more out of the multivariate analysis than we get out of this sort of univariate analysis of looking through at just specific peaks and seeing and summing them together to get more intensity. But yeah. Okay. So let me talk about biology a bit more and what we're doing in my group at the moment. Obviously, as somebody who's always worked in vacuum, be it in depositing coatings and analyzing them as well, we do a lot of biology work as well, but actually we tend to want to make things really simple. And for biology, creating model systems that represent our biology is really complex. And so what we want to do is sort of simplify our system, but what we don't want to create is the spherical cow of uniform density that we then put in a vacuum, because that's not it's too simplified. It doesn't actually represent the cow or the biology system in any real way. So it's a model, absolutely, but does it actually reproduce the biology we're interested in? So that's one of the things that I'm really curious about at the moment. And so if we want to create systems that replicate biology, these sort of cell mimetic systems and lipid vesicles are actually a really interesting way of looking at it. The outside of our cells is made up of this lipid environment, and these lipid vesicles are bilayers. They create these little beads, basically. And the challenge with looking at these lipid vesicles is that they're great models for cells, and they're great models for looking at cell surfaces, but if you've got a lipid vesicle floating around in solution, you can't actually analyze it all that easily. You need to use laser tweezers or something like that to actually locate them, hold them, and analyze them. So one of the ways that people want to look at lipid layers is to do a vesicle collapse, where we take the vesicle and collapse it onto the surface. But very few surfaces will actually enable you to do that collapse process. It's a spontaneous process. And so there's a huge amount of work that's gone on around understanding this vesicle collapse. It's all about the physical chemistry of the system and the curvature of the vesicle. But what I actually was interested in is, well, could I broaden out the number of surfaces that we actually had available, and could we use a surface interacting with a vesicle to create a system that would represent the surface of a cell? And so this is a chance to bring in some quartz crystal microbalance as well, because really can't just always be in vacuum. And so what we were interested in was how our lipid vesicles that are made up of DOPC, which is just a phosphatidylcholine lipid, it's commonly found in cell membranes, interact with our plasma polymers. So the first question was, could we use plasma polymers to actually make more diverse surfaces? And when you expose these lipid vesicles onto the surface of the acrylic acid surface. Sorry, this is quite sensitive to me moving my mouse. At pH 7, so we've taken our acrylic acid surface, we're in the QCM, we've got a flow cell, and we're flowing lipid vesicles over the top of the surface at pH 7. And you can see we expose the surface to pH 7 here at this point 1, and this is just the solution. So we can see that actually this is the frequency change. When we see a drop in frequency, that means we've added mass onto the surface. If we see a change in the dissipation, that's measuring the viscoelastic properties of our surface. So the interesting thing is at pH 7, just in this buffer, you add mass, and that's because you've actually added a little bit of swelling on the layer. When we add in sodium chloride into the system, you can see we get a bit more swelling as well, and we get a dissipation change that tells us the layer has become slightly more viscoelastic. It's now not just a rigid layer, it's actually done a bit of swelling. And then at this point 3, we add the vesicles, and you can see we get a little bit of absorption and a little bit of a dissipation rise and a little bit of absorption here. These units are actually very small. Okay, so they're very small amounts of adsorption. But the minute you have a vesicle on the surface, the minute you have a vesicle on the surface, obviously it's viscoelastic. It's a water bag, basically. So its viscoelastic properties are really soft. So the dissipation component rises. But you rinse in pH 7 and you can see you're holding some of those lipids on the surface. But the amount of material that goes on at pH 7 is really small. If instead we do our system, and you'll notice the frequency scale now has gone from being sub 10 to 325, and so has our dissipation scale has jumped to a large number as well. So now at stage 1, we're doing the same steps with those buffers. We just introduced some tris buffer at pH 4. We add the sodium chloride, and you can see a little bit of swelling when we add the sodium chloride at pH 4, but not as much as we saw before. And then at point 3, we introduce the vesicles, and suddenly we're getting a very large adsorption of vesicles directly onto this acrylic acid surface at pH 4. And at the same time, the dissipation component rises massively as well. So that tells us that we have absorbed a layer of intact vesicles directly onto our surface. So it's now like a layer of jelly sitting on top of our plasma polymer. And when we rinse this at pH 5, you can see that actually what we do is we rinse off some of those lipid vesicles as well, but we don't ever return. So the vesicles aren't attached tightly to the surface, and they can be rinsed back off on the large part, but we don't ever return to having no vesicles on the surface. So we end up with a few vesicles staying on our surface at that point. Now, the interesting thing is, if I take this pH, sorry, I've missed a point. We rinse here at pH 4. That's it here. At this point, there's no change. If we rinse at pH 7, what we actually see in this spike, sorry, I haven't presented this data for a little while. What we actually see is that, yes, the vesicles are leaving the surface, the surface mass comes down, and the dissipation comes down as well, indicating that now, rather than having vesicles on the surface, what we've got is the vesicle collapse on the surface, and we've validated this through other ways. So the vesicle now has actually opened up with that pH change. So that rinse at pH 7 has basically driven an osmotic change. Some of the vesicles have come off the surface, and there's no longer vesicles sitting on the surface because the surface has become more rigid in the dissipation component, but there's still mass on that surface, and that mass is associated with a layer of collapsed lipid bilayer on that surface. So what this showed us was that we could use different surface chemistries and use pH to derive vesicle collapse, but the pH was actually an important factor. And pH is an important factor because of the surface charge of the acrylic acid. At pH 4, it's neutral, so that allows the vesicle to go down onto the surface. And then at pH 7, the surface becomes slightly charged, but the vesicle also changes its characteristics. And that driver and that osmotic pressure with that change in pH actually drives the collapse of the vesicle onto the surface to create this monolayer. And what we found was that if we took an allylamine surface, we couldn't drive that change. So allylamine has an isoelectric point of around pH 9. And if we introduce vesicles at below that, the surface is obviously neutral charged or maybe even negatively charged, but above it, it becomes positively charged. But what we found was that the vesicles just stayed intact no matter what pH was on the surface, and they packed down really densely. And they weren't able to be rinsed off by any pH change either. So we've got a way, using these chemistries, of creating a packed vesicle layer, or by changing the chemistry and using that pH shift, we've got the way of actually, on an acrylic acid surface, making a vesicle, a monolayer, a lipid bilayer. And so the interesting thing here is if we use a FRAP technique, so we use fluorescence recovery after photobleaching, this tells us about whether the lipids are mobile on the surface. So here we photobleach an area. So we've got, in each of these lipids, we've actually got, my apologies, we've got some fluorescent tag. And if we photobleach an area of the surface, if the lipids are mobile within the vesicle, they'll actually be able to move through and recover the fluorescence in the area. But you can see here on the vesicle layer, it doesn't recover, telling us it's not mobile. But here on the acrylic acid surface, we photobleach, and after 5 minutes, the lipids are able to move around and we can recover. We can see a shadow of where we've photobleached, so it's not a perfect recovery, but lipid mobility is a really important characteristic if we want to create functional surfaces that replicate biology. Terry, how much longer have I got? When would you like me to stop?
Let's stop in about 5 minutes to give time for some questions.
Excellent. Okay, so I'll round up with this final take on some TOF-SIMS imaging. And so here, what we're looking at is using that micropattern surface. And so what we've done is put the micropatterning technique to work and created micropatterns of the amine and acid surface with a 10 nanometer pattern. And so these aren't particularly high resolution images. They're actually more focused on the elemental nature of the surface, but we can see that we've got patterns where we've got the acid on the surface and the background is the amine. Now, if you remember, the acid surface should induce a collapse, should enable us to induce a collapse of a lipid vesicle, while the amine surface should enable us just to have vesicles intact on the surface. And so what we did was then introduce our vesicles onto these arrays. And what you can see here is our lipids being patterned onto our acrylic acid and our allylamine system. But what we did was we took the same lipid and tagged it in one instance with a green label, and in the other instance with a red label. And so what this shows us is that we introduced the green labeled lipid onto the surface under the conditions that would enable it to attach to the acrylic acid. And then collapsed it, and then we introduced the other lipid, the red lipid, into the system to enable it to attach to the allylamine surface. So we're able to create that pattern of different lipids on the surface. And what we actually were able to show by photobleaching again was that the regions that we overlapped, and you could see that we've got migration of the lipid in the regions between, but where we've crossed over and photo bleached the areas that are sitting here that are the red lipid, there is no mobility. So the area of green where the lipid's able to move around is mobile, but up on the pillars or up on the actual surface areas that are the different chemistry, the red zone where the red lipids are, they're not able to recover. They stay dark. So we've retained that mobility, and now we can have an area of mobile lipids sitting next to an area of immobile vesicle as well. So that's just a different way of putting these systems together. Which is a nice demonstration of how you can bring the chemistries together to control the structures of the biomolecules, and in this case, the lipid structures on the surface. So I think I'll leave it there. I won't go into our current work on 3D systems simply because I think it's taking it a step too far. But what I will do is just mention at this point that this work was sponsored through the Australian Research Council. There's also work I've shown here that was sponsored from work that I did in the UK, that was sponsored by the Engineering and Physical Sciences Research Council in the UK, and a number of other trusts and foundations that have supported our work. The team that has done this work is ranged across the whole world actually now. This is work that's been done by Hannah Askew, who is now at the University of Sheffield working there in commercialisation, by Gautam Mishra, who now works for 3M in Germany, and by Simon, I've just lost the surname, and Simon Moulton, who now works in industry in the UK as well. So thank you so much for your time, and thank you so much for the opportunity to speak today. I'm happy to take any questions.
All right, do we have any questions?
I might just drop off that and stop sharing. And actually see faces, even if they're masked.
I have one question. Do you have to modify the time-of-flight SIMS instruments to work with these biomolecules?
No, not at all. And we do all of our work directly using the standard mode. So we're not freeze drying or anything complicated like that. This is all standard analysis. Okay. This is all done. All the instruments I've used in the recent past have been the iron TOF instruments. And most of this work is actually done with the old bismuth sources as well. So it's not the argon clusters or anything complex like that yet.
Okay. So is there any, you mentioned some of your former people were working in commercialization.
Yep.
Can you mass produce these, or?
Yeah. You can. I mean, I think, and that was one of our thinking when we actually picked up using photolithography, is that, you know, that's a fairly standard technique in the semicon that's scalable, absolutely scalable. And that's one of its more advantages, is there are other ways of patterning plasma polymers with physical masks and things like that. You don't get the pattern resolution as well, because it's a gas phase process. So every time you've got to bring a physical mask into contact, life gets a little more complicated. But, you know, one of our reasons for really pushing this and the EBL work was that they're readily scalable and integrated. And because everything's gas phase, you know, it's all vacuum processes if you need it to be. And obviously there's also plasma polymerisation that's now done in atmospheric as well, which I think is another really interesting phase to think about how this would work there too. Is that a Luke? Hi, Luke. We're not hearing you, Luke.
He's got to turn on his own mic, I think.
Yeah.
How about now? Can you hear me?
Yes, now we hear you.
Hey, how you doing? So I wanted to ask you, thank you. It was a very nice seminar. I had a couple of my students sign in. I was wondering, you know, the plasma polymers, as you know, they have some fair number of radicals in them, and they have aging issues. Has that been much of a problem with the work you've been doing, or not?
No,
really?
It's really interesting. The whole aging of plasma polymers question is a really interesting one. it seems to vary significantly depending on the type of reactor you use and the style of your reactor. Some of them seem to create a hell of a lot more radicals that are long-lived. So all the work from Thomas Gengenbach in CSIRO, they're quite a different reactor style. We see radicals and we definitely see aging, but we've actually shelf stored all of our tetraglymes and they don't age. They're still protein resistant out to a couple of 100 days. We can pull them off the shelf and they're fine. They work. The maleic anhydrides are obviously a slightly different issue because they will hydrolyze if you're not careful. So they are going to not be but that's not about the radicals. That's about the chemistry more than anything else, and the reactivity of the system. For a lot of our systems, I would recommend with an amine, obviously, yes, you can't really stop them aging. They are still have reactivity in them. We did a whole heap of work looking at this using NexSAFs actually back in the day. And the way we deposit them, the rate at which we deposit them, I think also has an issue here. It has an interaction as well. Our reactors are stainless steel tubes with internal electrodes. They're not externally done, and we're not putting them downstream. So I think there's a whole range of processes that go on with these plasma polymers, and we've noticed that the rate of deposition is also really important. The slower you deposit, the slower the growth rate of your plasma polymer, the less post-oxidation you get.
Oh, okay.
So I don't know whether it's just you exhaust those in the system as you go, but that's definitely stuff we've seen in our systems. Yeah.
Hey, thanks.
No worries.
All right, do we have any other questions? Well, if not, let's remember to thank our speaker, and we do that by typing applause into the chat window. Applause, applause. Thank you very much.
Thank you all. Have a good evening.
Early today. We greatly appreciate you coming to this. And I'd like to thank everybody who comes to these seminars as well. I was a little worried that we might lose crowd over the summer, but we had our highest number of people on at this one. So thanks everybody for coming.
Excellent. And I do invite you, if you're bored and lonely at pandemic prime time, and to join. We have the Australian Society for Biomaterials has a seminar every Wednesday afternoon. It's on at now, it's prime time. So it's 1 p.m. in Western Australia, 3 p.m. in Victoria or on the eastern states, and then 5 p.m. in New Zealand. I have no idea what time that is where you are, but it's a great talk series of people who are interested in bio-related materials as well. So you can go to the Australian Society for Biomaterials and look that up if you're interested. Luke can tell you we're a delightful gang. He's been here as the guest speaker in our dim dark past.
Not recently, but yes, it's a
dim dark past.
They have a wonderful biomaterials effort down there. So
if you send me a link, I'll pass it out to everyone.
Okay, I will. No worries.
Well, thank you so much for coming and appreciate it, everyone. And I just want to remind everybody, our next month will be Professor Rachel Oliver, and the time will be shifted 1 hour because she's in the UK, and that way she won't have to talk at midnight. So we'll be 1 hour earlier next month, and we look forward to that talk and look forward to seeing everybody then.
Bye.
Thank you.
Thank you so much for inviting me, Jeff, and lovely to not see you.
Yes, hopefully we'll see each other again soon.
Thank you.
All right.
Okay, bye.
All right, bye-bye, everybody.